Right, so it might seem like a really good idea that you can have a possibility to have multiple languages on top of the JVM, where all of them are being compiled and then translated to some standard bytecode format. It's all the same class file, and the only thing that the JVM needs to do is actually to check that this complies with the bytecode format that it accepts, that everything is correct over there, and then it can just run it. It seems like a really convenient thing to have this possibility to host so many different languages. Well, actually, at the start, it wasn't designed with this idea in mind. It was actually designed purely for Java. And it means that because Java has some kind of ideology, JVM also has some limitations, and I'm going to tell you a bit about this. So Java is a statically typed language. Here we can see on the left what statically typed languages do and dynamically typed languages. It means that at compilation, during compilation, all the types are being checked. So if some types are incorrect, the compilation will not work out. And during runtime, there will be no surprises with types. So all the types already should be good in the bytecode in the class file. And for dynamically typed languages, it might be that we don't even specify any types in the code at all. And then during runtime, we might get some surprises because for dynamically typed languages, we're checking that at runtime, the values that we're actually having, they correspond to the types that are expected in this situation. And we might think that, okay, with this idea, then probably it's not possible to build a dynamically typed language on top of JVM because, hey, everything is checked and class file should have all the types there already. In fact, there are dynamically typed languages that are built on JVM, and these are just some examples. There are more of them, and they indeed had to deal with quite some limitations and workarounds to achieve that. For example, let's take a look at this bit of code. So we're not specifying the return type here. We're not specifying the type of the argument in the function. We just assume that this, whatever we are getting as argument, has this ABS function. And at runtime, we can run it with -1, it will be successful, and we can run it with a string value, and it will fail at runtime. So if we want to build a language that looks like this on top of JVM, how should we actually design it? One of the possible workarounds is, it's not a very easy workaround, but it is creating kind of a super type that is more global type that will be basically your type for everything, for every type in your language. And this is how it would look under the hood, right? And you would just implement all the possible functions that you possibly can have on any type there. And then you will need to take care of some casting of the values from Java types to this type. And of course, it's a lot of pain in the neck. And it's really hard to predict what functions and what methods you would like to have for each type in advance. So it's really hard, and it's not the best approach. There are also more approaches that were used, so they involve reflection, they involve some extra interpreters that run on top of JVM, but they also have their limitations and they're also quite slow. So what was introduced in JDK 7 was a new instruction, invokedynamic. It's the bytecode instruction that helps to support these dynamically typed languages that are being built on top of JVM. And basically, they had most of the problem when they were trying to invoke methods because they need to know what type owns this method, and all the types should be known in advance. So how is this different? So these are some other instructions for invoking the methods. There are more. There is also invoke special, invoke interface, but these are good for illustrating what I mean. So invoke virtual is meant for invoking the method on some instance of some class, right? So here we're putting the value that we provide as argument. We also must put the reference to that instance on top of the operand stack before we use invoke virtual. And then when we use invoke virtual instruction, we must specify where this method actually is located that we're calling. So it belongs to print stream type. We also need to specify the name of the method and all the types that it accepts. So it accepts the string and also what it returns void. And this should be all specified in the bytecode. For invoke static is pretty much the same. This is for invoking the static methods, and the difference is that we only need to put the arguments on top of operand stack before we invoke it. We don't need to provide any instance because it's a static method. We still need to specify what is the type where this method is located. So inside string class, we have value of method that accepts integer and returns string. What is different about invokedynamic? So we do need still to load all the arguments before that, but for invokedynamic, we don't need to specify where this is located or what is even the function name. This is not necessary. We need to specify only that, okay, we want to invoke something that accepts integer and returns string. It's an example, but like we only need to specify the type that we're interested in, the type of this target function or method. And actually, we're pointing with the reference number 0 to some other section in the bytecode. And in this section, we're specifying the bootstrap method. And the bootstrap method is responsible for choosing at runtime what function to invoke. And we can provide some arguments, and most of the arguments are filled by JVM, but I will show a bit more about this. So how does it work? When JVM runs the bytecode, when it meets the invokedynamic instruction, it goes to this bootstrap method that is specified in the bytecode as well. The method handle will do some logic. It can generate things, it can look up things, and it will choose the target method that it wants to invoke, and it will choose the method handle. Method handle is basically the mechanism that is similar to reflection. It will just have a direct reference to the method to invoke. Then it will link this invokedynamic instruction to this target method, so this job will not have to be done again when we meet again this instruction. So next time when we go there, we will directly invoke that target method in the same circumstance if nothing changes. And this was very nice for supporting the dynamically typed languages. But you might be thinking, how is it related to Java at all? Well, let me prove you that statically typed languages can also be quite scary. So Java is actually using the invokedynamic instruction a lot when we do Java compilation, when we use Java compiler. And I want to show you some use cases where this is done. So first of them is string concatenation, where you, in this case, where basically for some use cases we can have somewhat faster implementation of string concatenation. Because, yeah, if we are concatenating some constant values, the whole concatenation will be optimized away. If we are concatenating some variables that are not final, we might actually we are using invokedynamic in this case. So this example, we have two strings, and we are putting them onto the operand stack, and then we have invokedynamic instruction where we are only specifying, okay, the target method will need to accept two strings, and it will need to return a string. Then we specify the bootstrap method. This is located in string concat factory, in make concat with constants. It accepts a lot of different arguments. Most of them are provided by JVM, and we are providing also another argument to this bootstrap method, which is basically a string template, which contains like two placeholders for our two values. And what is happening during runtime is inside of our bootstrap method, there is a logic that is, okay, in this case, we have two elements. They're both parameters, not some constant values or whatever. They're both some instances of some object, and they're not, so they're not primitive, and they're also not null. And for this case, okay, we are going to look up a method that is called simple concat. So there will be some method handle lookup somewhere else in the code, and in the end, we will end up with this function that is called simple concat. And this is the fast path for this specific use case. There can be unary concatenation, binary concatenation that goes fast through some different implementations. And in case we don't fall under any of this, we'll just go to some more slow maybe approach, but at least it gives us a possibility to dynamically decide what is the faster approach here. Another example of invokedynamic is when Java uses invokedynamic is pattern matching for switch. It's the new pattern matching where we already have possibility to switch over different types. So this involves a lot of logic also related to when we have guard conditions, then there will be repeated types and some extra integer variable that is involved in all these calculations. So how is it done under the hood? So we have invokedynamic instruction, which points to a bootstrap method type switch, and it will have to look up the method that basically needs to return an index. And that index will help us to find the location in the bytecode where we have to jump next to execute some block of code. So the only task of it is to return an index, and we provide to the bootstrap method also some arguments, basically a list of all the types that we are switching over. And internally, it will just do some checks for each type. It will look up the method handles of these methods that do the checks. It will combine them into a chain, and it will execute this all at runtime as one dynamic decision-making logic, and it will find this index based on these checks. And this helps us to abstract away this logic from our bytecode, so it is all dynamically decided. Our bytecode stays a bit cleaner and doesn't contain like just the language logic inside. And I think the most exciting case when we're using invokedynamic in Java is lambdas. So for lambdas, we are basically specifying the implementation of the functional interface as our lambda body, right? So functional interface is the interface with one abstract method, and we're specifying what is the implementation of this abstract method. What is actually happening internally is that during runtime, there is a class created, the synthetic class, that implements this functional interface. And the implementation of that one method is going to be whatever we specify as the body. And in this case, it's just the reference to a method println, right? But it also can be some bigger block of code. During compilation, it will be placed in a separate method internally, and it will be pointing to this method here. So the purpose of this target method that we're looking up here is to return us the instances, in this case, of something that implements consumer with the println function. And then we can take this consumer and provide it to for each, and yeah, then it will just continue normally. So what is the exciting part here is that we don't end up creating any extra classes during compilation. There's actually a synthetic class created during runtime. We don't even ever see it, and it will only be created in case we hit this lambda, and it will take less space and be quite performant. So to sum up what I've said, why is it even done for Java? Well, because it helps to reduce the complexity of the bytecode, to abstract away the decision-making to runtime. It saves the space because our bytecode doesn't have all this logic, and the new language features are bringing more and more complexity, so of course we don't want to keep it all in our bytecode. Implementation of these language features can improve from version to version, and we might not even notice that something changed. So in our bytecode, everything stays the same. We don't need to rebuild the project or recompile to benefit from the new features. So this all can be then changed without us even noticing. In fact, I was looking at Java 21 early access, and the type switch, the switch case implementation was completely different than when it was actually released for real. Of course, I think predictability of our program can be a bit less, maybe, because a new implementation can possibly create more instances of for string concatenation of string and put them on the heap, or less. It depends on what is the current implementation. The performance can become better because, of course, they are working on performance all the time. So I really enjoyed reading the article on the left. If you're curious about the topic, I learned a lot from it. And on the right, there is a link to my blog, because I like to write a lot of things about JVM. I like to torture JVM, and my Twitter handle is below. So if you're interested, you can take a look. And yeah, thank you. That was it from my side.